Hi, good afternoon. My name is Shivani. I'm one of the new Wyzant tutors here, and I'm here to help you with a calculus rate of change problem. So, looks like this problem involves a 25-foot long ladder leaning against the wall of a house, and the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So that means it's increasing at a rate of 2 feet per second. And it looks like we need to calculate. So let's start with part one. Calculate the velocity of the top of the ladder when the base is 15, 20, and 24 feet away from the wall. So basically, we're calculating. So if you think of it conceptually, as the base of the ladder slides away at 2 feet per second, the side of the ladder which is leading against the house is going to decrease at some rate. Now, based on the Pythagorean theorem, we can infer that x squared plus y squared is 25 squared, or 625. So we can derive an expression for this vertical length y in terms of the horizontal length x. So this means that y squared is equal to 625 minus x squared, and y is equal to 625, or square root of 625 minus x squared. And based on this expression for y in terms of x, we can determine dy over dx. So let me just write down some definitions here first. So dy over dx is the rate of change of the vertical side, y, in terms of the horizontal side, x. dy over dt is the rate of change of the vertical side, y. Let me move this. With respect to time in seconds. And then dx over dt, which in this case is 2 feet per second, is the rate of change of the horizontal side, x, with respect to time in seconds. All right, so these are just some key definitions which I want you to think about as we move on through the problem. Let me see if I can make this smaller. Here. Right. All right, there we go. So with this in mind, let's now find dy over dx given our expression. So we need to find dy over dx using the chain rule. So we can rewrite this expression as a fractional exponent. So y is equal to 625 minus x squared raised to the 1/2 power. So now we can use the chain rule to determine dy over dx. So for the chain rule, we need to pick, I usually like using u substitution. So u is the value of the inner function, which is 625 minus 625 minus x squared. So du over dx is equal to 0, or the derivative of 625 minus 2x, which is the derivative of x squared, which is negative 2x. So now we have y is equal, or dy over dx is equal to d over dx of 625 minus x squared raised to the 1/2 power. And we can do u substitution since we substituted u to be 625 minus x squared. Dy over dx is equal to d over dx u raised to the power 1/2. Now we can rewrite that using u. So in terms of the derivative of u, so this would be equal to d over d u of u raised to the 1/2 power times d u over dx. So now we can take the derivative of u 1/2. So recall that the 1/2 exponent is the outer function, and then du over dx here is going to be this negative 2x. So when we substitute the values here, we have dy over dx is equal to, so for this portion right here, we will be using the power rule. So d over du of u raised to the 1/2 power would be 1/2 times u raised to the power 1/2 minus 1, which would be negative 1/2 times du over dx, which is negative 2x. So dy over dx would be equal to, so here 2 and 2 can cancel out. So you would have negative x, or sorry, let me substitute u first. Okay, so let's first substitute u. So back to this step, we have 1/2 times u raised to the negative 1/2 power times negative 2x. So that would be 1/2 times 625 minus x squared raised to the negative 1/2 power times negative 2x. So that would be 1/2 square root of 625 minus x squared times the negative 2x. And then right here, you can cancel out the negative, the 2's. So the 2 cancels out, and you will be left dy over dx would be negative x over the square root of 625 minus x squared. Now this expression right here, the dy over dx, if we go back to our definitions, it represents the rate of change of the vertical side y with respect to the horizontal side x. So now that we have dy over dx, we can obtain an expression for dy over dt, which is the rate of change of the vertical side with respect to time. So it's going to open up another board here. So dy over dt, let me use a different color here. Right. So dy over dt is equal to dy over dx times dx over dt. Notice when we derive this expression, notice how the dx's cancel out, and you're left with the dy on the top, the numerator, and the dt at the denominator. So I just wanted to point that out. So going back to our problem, dx over dt is the rate of change of the horizontal side with respect to time, which is 2 feet per second, if you recall in the problem. So the question is basically asking us to calculate dy over dt, the rate of change of the horizontal side when the base is at 15, 20, and 24 feet away from the wall. So let's start off with calculating dy over dt when the base is 15 feet away from the wall. So when x over here is equal to 15, 20, and 24. I'm just going to write that down here. So when x is equal to 15, we can calculate dy over dt when x equals 15 feet. So we can simply substitute dy over dx and then dx over dt, which is 2 feet per second. So dy over dt is equal to dy over dx, which we calculated to be negative x over 625 minus x squared. Or, sorry, square root of 625 minus x squared. So that would be equal to, so we substitute 15 for x, negative 15 over square root of 625 minus 15 squared times dx over dt, which is 2, because that represents the 2 feet per second. So when we plug all this into our calculator, let's see what we get for dy over dt. Let me just calculate this real quick. All right, so I got negative 1.5, and the units are feet per second. Now the results make sense because you would expect that as the base of the ladder is pulled away from the wall, this vertical distance y is going to decrease. So that's why the rate's negative. Now we can do the same types of calculations of dy over dt when x equals 20 and x equals 24. So dy over dt is equal to negative x over root 625 minus x squared. So it'll be negative 20 over root 625 minus 20 squared times 2, which is dx over dt, 2 feet per second. So when we plug this into the calculator, let's see what we get. So we get negative 2.67 feet per second. Or actually, let me give the exact value. The exact value is negative 8 over 3. Negative 8 over 3 feet per second. And lastly, let's calculate dy over dt when x equals 24 feet. So it'll be negative 24 over square root of 625 minus 24 squared times 2. It's gonna circle this and show that it's dx over dt, just so that you don't get confused. Okay, so dy over dt when x equals 24, negative 24 over square root of 625 minus 24 squared times 2. So let's calculate that. Okay, so the exact value we get here is negative 48 over 7 feet per second. All right, so that concludes the first part of this problem. So let's move on to the second part of this question, which is consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 20 feet from the wall. Okay, so the area of a triangle, if you recall, it is it's just going to be 1/2 times x times y. So 1/2 times base times height of the triangle. So we can express the area, which we're going to call A, as purely as a function of x. Now, if you recall this equation right here, x squared plus y squared is 625. We already determined an expression for y in terms of x right here, that y is equal to square root of 625 minus x squared. So we can rewrite the area formula as follows. A is equal to 1/2 times x times the square root of 625 minus x squared. Because we substituted that expression for y. So before I move on, I'm just going to write down some rate definitions similar to how I did for the first problem. So dA over dt is the rate of change of the triangle's area with respect to time, which will be in seconds. And then dx over dt, which is 2 feet per second, and that's the rate of change of the horizontal side, x, with respect to the time in seconds. And then we have dA over dx, which is the rate of change of the triangle's area with respect to the horizontal side. So, like with the previous problem, I want you to keep these definitions in mind as we move through. So now that we have an expression for the area in terms of x, we can calculate dA over dx, the rate of change of the area with respect to the side x. So here we would use the product rule. So dA over dx, so it's equal to 1/2 x times the derivative of root 625 minus x squared plus root 625 minus x squared times the derivative of 1/2 x. So an easy way to remember the product rule is 1 times the derivative of 2 plus 2 times the derivative of 1. So going back to our previous problem, so if you recall, d over dx of root 625 minus x squared, we calculated that to be negative x over root 625 minus x squared, because if you remember, we set up y to equal root 625 minus x squared. We found the derivative of that to be negative x over root 625 minus x squared. So we could go ahead and plug that in here. So dA over dx is equal to 1/2 x times negative x over root 625 minus x squared plus root 625 minus x squared, and the derivative of 1/2 x is going to be 1/2. So the question is asking us to find, the question's asking us to find the rate at which the area of the triangle changes when the base of the ladder is 20 feet from the wall. So that means x is equal to 20 feet in this scenario. So using x equals 20, we can calculate dA over dx when x is equal to 20. So dA over dx when x equals 20, simply plug and chug. So we got 1/2 times 20, which is going to be 10 times negative 20 over square root of 625 minus 20 squared plus square root of 625 minus 20 squared. Oh, sorry. This is just supposed to be 1/2, not 1/2 x. Okay. All right, so we plugged and chugged 20 into this equation, and then let me see if I can simplify it further before I plug it into my calculator. All right, so now let's plug and chug this into the calculator and see what we get. So dA over dx is negative 5.8333. So let me see what the exact value of this would be real quick. So this would be negative 5 and 5/6. So let's see. Yeah, negative 35 over 6. All right, so we got dA over dx. So now dA over dt. Now the question's basically asking for dA over dt, the rate of change of the area with respect to time when the base x is 20 feet. So dA over dx, or sorry, dA over dt is equal to dA over dx times dx over dt. Now again, I want you to notice how the dx's cancel out. You're left with dA on the top and dt on the bottom. So now we can go ahead and calculate dA over dt when the base is 20 feet from the wall. So that would be, so dA over dx, we calculated it to be negative 35 over 6. And dx over dt is 2 feet per second. So we have negative 35 over 3, and the units are going to be area over time, so square feet per second. So that would be our final answer for this part 2. So basically what this means is that when this base is 20 feet, the area is decreasing at a rate of 35 over 3 square feet per second. So that's approximately 11.7 square feet per second. So let's move on to the third part of the problem. Find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 20 feet from the wall. Okay, so here's my setup right here. So this right here is the angle theta. I'm just gonna draw it in red. The angle theta between the ladder and the wall of the house. And X, the base here is 20 feet. So let me just mark that here real quick. Now we can derive an expression for theta in terms of X. So the sine of theta is the opposite over the hypotenuse, which is X over 25. So that means that theta is going to be equal to the inverse sine of X over 25. And again, I'm going to write down some definitions before we proceed with the problem. So d theta over dt angle theta with respect to time. D theta over dx that's going to be equal to the rate of change of angle theta with respect to the horizontal side x. And then dx over dt, that's 2 feet per second, the rate of change of the horizontal side x with respect to time in seconds. Right. All right, so now we can determine an expression for d theta over dx. So for this, again, we need to use the chain rule. So u is going to be our inner function, x over 25, which we can rewrite as 1 over 25x, just so you could clearly see the 1 over 25 coefficient. And then du over dx is equal to 1 over 25. So d theta over dx is equal to d over dx inverse sine of x over 25. So d theta over dx is equal to d over du sine -1, so inverse sine of u times du over dx. Now, the derivative of the inverse sine, that would be, so d over du sine -1u will be 1 over square root of 1 minus u squared times du over dx. So now we can go ahead and substitute u and du over dx. So that would be 1 over the square root of 1 minus x over 25 squared times 1 over 25. So d theta over dx is equal to 1 over square root of 1 minus x squared over 625 times 1 over 25. So d theta over dx would be equal to 1 over 25 times the square root of 1 minus x squared over 625. All right, so we got the expression for d theta over dx. So now we can obtain an expression for d theta over dt in terms of d theta over dx and dx over dt. So d theta over dt is equal to d theta over dx times dx over dt. And going back to the question real quick, we find the rate at which the angle is changing when x, or the base of the ladder, is 20 feet from the wall. So it's going to open up another board here. So d theta over dt when x is equal to 20. Sorry, let me go back to the previous board. So it would be 1, it would be d theta over dx. It would be 1 over 25 square root of 1 minus x squared over 625 times dx over dt. So now we can substitute 20 for x and then 2 for dx over dt, since x, the horizontal side, is increasing at a rate of 2 feet per second. Let me double check this. Oh, that's where I went wrong. It's supposed to be 15 over 25. Yeah, because the square root of 225 over 625 is 15 over 25. That's where I went wrong. Okay, so if this is the case, it would be... So let me just double check this real quick. So 1 over 25, square root of 1 minus 20 squared over 625 times 2 would be 2 over 25 times the square root of 1 minus 400 over 625. So it'll be 2 over 25 times the square root of 225 over 625. So it'll be 2 over 25 times 15 over 25. So down here, 25 and 25 cancel out, so you're left with 2 over 15. All right, so 2 over 15 is our final answer. And the units of our answer, let me pick a different color. So d theta over dt is equal to 2 over 15 radians per second. All right, so these are our final answers. So going back to our problem, final answer for question 1 would be, let's see. All right, so for number 1, A, B, and C, so for the first one, you have negative 1.5. Or 20 feet away from the wall, you have negative 8/3 feet per second. For part B, the answer was, let's see, negative 35/3 square feet per second. And the answer to C was 2/15 radians per second. And let's go back. So this is actually an increase. So, and that makes sense because if you think of it, as the ladder slides down, this angle is going to get larger. So it's going to increase at 2/15 radians per second. All right, so that pretty much wraps up the answers and the explanations. If you have any questions, feel free to leave a comment in the comment section. Thank you and have a wonderful day.